K-means is such a nice algorithm. After we learned about Weka and its basic operations to organize, visualize, and pre-process the data, and of course, after we learned the K-means algorithm, now it's time to implement it in Weka. We will go back to the HCC dataset, and this time we will apply K-means. We will go to the cluster page, and under clusterer, we will choose simple K-means. In this implementation of K-means in Weka, the default value of K, the number of clusters, is 2. We can change it, of course, but for now we will keep this number. The only thing that keeps us away from applying K-means now is clicking on Start. Let's see the results. They appear in the clusterer output window. I'm going up and see the run information. 50 attributes were used. It took K-means 6 iterations to converge. The quality of the clustering here is calculated as the sum of squared errors. That means the sum of intra-cluster distances. Here are the initial starting points, which were random. For cluster 0, the starting point was 1 for the first attribute, 1 for the second attribute, 1 for the third attribute, 0 for the fourth attribute, and so on. While for cluster 1, the starting point was 1 for the first attribute, 0 for the second attribute, and so on. As you can see here, missing values were replaced with the average of their surroundings. Next is the final clustered centroids. For each attribute, you can see the separation between cluster 0 and cluster 1. As we know, it is a very fast algorithm. It took 0.01 seconds to run. 63 records were put in cluster 0 and 102 put in cluster 1. We can use the visualization model in order to see the clusters in our eyes. Right-click on this run and click Visualize Cluster Assignments. Let's maximize the window, and as we showed before, we can pick a certain attribute here, another attribute here, and this time the color is selected by the cluster. We can see here at the bottom that cluster 0 is blue and cluster 1 is red. As we can see, the separation into two clusters is not very obvious from this chart. We can use this bar to change the X and Y axes. Let's change X to this and Y to this, and still the separation is not very clear. I'll try to explain why actually with another question. Let's zoom in on this part by choosing rectangle here, drawing the rectangle, and submitting it. And my question is as follows. We know that in K-means, each data point is classified to the closest centroid. So how come we can see here group of points, some of them are blue, that belong to one cluster, and some of them are red, that belong to another cluster? How can it be that wherever the centroids are, there is no clear distinction between the colors of the points according to their values? Well, the answer for that is that we as humans, since we cannot see more than 2 or 3 dimensions, cannot see the effect of the other attributes or dimensions. In this case, we have 50 of them. So just imagine that the blue points are on the screen surface, while the red points are much closer to your face. So it doesn't really make sense to look at clustering results this way. Let's try to make it simpler by focusing only on a few attributes. Later, we will see a few interesting alternatives that enable us to make sense even with a large number of attributes. For now, let's go back to the pre-process page and select only 3 attributes: ALT, AST, and GGT. After all, we are talking about hepatocellular carcinoma. We want to focus only on these 3, therefore we will invert the selection and remove all the other attributes. Voila! Let's try to cluster now. I will choose again simple k-means and run it. Let's look at the results by right-clicking on this run and choosing Visualize Cluster Assignments. Okay, maybe this makes more sense. Notice that after this run of the k-means algorithm, we have 2 new variables. Let's see them here. In addition to the ALT, AST, and GGT attributes, the clustering process added an instance number, which is just a serial number, and the cluster. So now actually the default is that the x-axis is the instance number. This is of no interest to us. Let's change it to AST. So now this chart plots AST versus ALT and differentiates between the 2 clusters by color: blue to cluster 0 and red to cluster 1. Already we can see here that clustering was made in a nice way. Most of the records with low values for AST and ALT belong to cluster 1, while records with higher values belong to cluster 0. We can play a bit with the axis. Let's change X to be GGT. The separation is even clearer. And maybe Y for AST. Yes, that really makes sense. We can see 2 archetypes of liver enzymes with low values and high values. That's good. Well, mathematically speaking. But what is it good for? Let's see. Let's try to repeat this process while looking how much these groups correspond to one of the other attributes in the dataset, let's say the symptoms. I will close this window, go back to the pre-process, and repeat my selection of attributes, so I will leave also the symptoms one. I will not go over the whole process again, let's just do it by magic. This is a video lesson after all. Here we go. Now we have also the symptoms attribute. Let's try to repeat the clustering process, first in a naive way, keeping the same algorithm and clicking Start. We will now visualize it. Pick, for example, ALT for the x-axis, Y is still the symptoms, and the color is the cluster. So that looks amazing. All the blue data points appear here, where symptoms is 1, and all the red data points appear here, where symptoms is 0. So it's like the clusters succeeded in separating all data points in a way that predicts the symptoms. Well, not really. We did here a very common mistake. The mistake is that we included the symptoms attribute in the clustering process itself. And this attribute is actually nominal, having only 2 values in a very clear and clean way. So no wonder the computed clusters got aligned with this attribute. What we need to do is go back and state here with this button which attributes to ignore. I will select symptoms and rerun the clustering process. This actually reconstructed the same clusters that we had before when we didn't include the symptoms attribute. How do I know that? In the results list, I will go back now to the first run. I will click it. And as you can see, all the values here are actually the same. Let's compare it to the third run again. Nothing is really changed except the information about the ignore attribute. Okay, let's again visualize this one. Now the picture is not as beautiful, but more authentic. Let's choose AST for X, GGT for Y. So these are the 2 clusters. And if I change the color for symptoms, I see that some points did not change color while others did. Looking at it visually is not good enough, of course. We want some metrics that determines the overlap between the computed clusters and the symptoms. Weka can do that as well. I will close this window, and in cluster mode, instead of just using the training set as a whole, this is the dataset that we downloaded, we will choose the classes to clusters evaluation. What this option enables us to do is to pick again the symptoms as a class, as a criterion, and to compare the clusters to it. We don't even need to say again that we need to ignore this attribute. Let's click Start. And here we see that the symptom value of 1 was assigned to cluster 1 mostly, but also to cluster 0. And this is the separation of the 0 value of symptoms. Overall, there are 66 incorrectly clustered instances, or 40%. Obviously, 40% is a very high number. If we just run a random clustering separation, we will get approximately 50%. So 40% is just a bit below that, just a bit below randomness. But does that mean that ALT, AST, and GGT can or cannot predict symptoms? Well, as I said in the lecture, many times k-means makes mistakes. I also said that many times when you run k-means again, you can get different results. So at this point, I would like to show you another button in Weka. Actually, this is like a hidden button. I don't know why they designed it this way. If I left click on this area, I can edit the process of this object, the clustering method. Here it is. This window actually shows me a lot of information about the tiny details of the algorithm that I'm running. The About field tells us a bit about the algorithm. If I click more, I get more information and some explanations about the different fields that appear later on. This is a good way to learn about the tiny details and all the parameters that affect the result of any algorithm that we run in Weka. One of the most important fields is the number of clusters, the K of k-means. In this case, 2 is okay, this is also the default, but what we will want to do now is to change seed. As you can see, it is the random number seed to be used. We know that k-means picks the initial centroids by random. When the seed is 10, this is the default, it means that we have a certain set of random numbers, and if we change the seed, and we can change it to anything, let's say 11, it means that we will use a different set of random numbers. We will click OK and rerun k-means. Voila! What used to be 40% now is 38%. Let's do it again with another seed. 12 this time. Rerun the algorithm. We are back at 40. Let's change it now to our lucky number. Let's say 70. Run it again. And now we got 37. Well, this is not such a good scenario. Another thing that we can do, and this is what's so nice about Weka, is that very easily we can test other algorithms. Although we didn't learn them in the lecture, feel free to choose one of the other methods detailed here. Let's say hierarchical clusterer. If you want to learn more about this, click on the hidden button and click More. I will start, and now we got 32%, and so on. We can continue playing with these algorithms and their parameters. Maybe it will help, maybe not. But now, if we have this empiric method to quantify how good our clusters are, or how predictive they are, we don't need to focus again only on 3 variables. Let's go back to the pre-process page and add all the other attributes that we removed. Again, I will do it by magic. Voila! Now we have everything as we had in the beginning. We will go to cluster again, select the symptoms as the class we want to compare to the clusters. Here it is. Go back to the last k-means run and the best one we had so far with 37%. We will now rerun the k-means algorithm, but this time with much more data. So let's see, we had 37%. Now we have only 32%. So generally, more data, the better. There are many more things you can do with unsupervised machine learning and clustering algorithms specifically. Weka is a wonderful platform to learn such algorithms, to play with them, and solve some challenges in a very easy and pragmatic way. But now it's time to move from unsupervised to supervised machine learning.